All right, after completing the lesson from last time, we learned how we can use radians and degrees to measure angles and find distances around a circle and talk about velocities, linear and angular, and also find circumference, parts of circumference called arc length, or areas of sectors. Today, we're going to go into what's called right triangle trigonometry, and you're probably much more familiar with this, having probably done it in Mrs. Mage's class a year ago, or also integrated 3, you may have touched on it. But right triangle trig is really what we're used to seeing with sine, cosine, and tangent. Now, right triangle trig, obviously, you must have a right triangle. Obviously, the two legs are the two sides that make the right triangle or the right angle, that is, are legs. And the third side we call the hypotenuse. That is always the side opposite the right angle. Okay, knowing this, we can talk about SOHCAHTOA, and it's spelled wrong here. SOHCAHTOA. And what this means is that the sine of theta is actually opposite side over the hypotenuse. So opposite the angle theta, whatever side that is, over the hypotenuse. That's the ratio. The cosine of angle theta is equal to the adjacent over the hypotenuse. And the tangent then is the opposite over the adjacent. So if you look at these letters that lead the fraction or the ratio, we can see that it spells SOHCAHTOA. And if we just memorize SOHCAHTOA, we know the ratios, so we can set up any right triangle trig problem. So we have this triangle here with theta being located to our right. The 90-degree angle is there. So we have 12 and 13. Well, this is a leg and a hypotenuse. So we have to, find the other leg. Now, we can use Pythagorean theorem. I think we probably are familiar with the fact that a 5, 12, 13 is a Pythagorean triple, but I'm going to go ahead and work it out. So a squared equals 25. So indeed, a is 5. So from this then, we can find the 6 trigonometric functions of the angle theta. Now, what do I mean by that? Okay, so if we look at this then, 5 is the adjacent side because it's next to the angle. This is always called the hypotenuse, obviously, and then the opposite side is opposite the angle, so that is 12. So this is opposite, hypotenuse, and adjacent. So I'm going to redraw it here. Here's my right triangle. This is 5, 12, 13. This is the hypotenuse. This is theta right there. So this is opposite, and this is adjacent. So if I use SOHCAHTOA, and I set up the 6 trig functions, the sine of theta then would be opposite over hypotenuse. The cosine of theta would be adjacent over hypotenuse, and then the tangent of theta would be the opposite over the adjacent. So now you can obviously guess what cosecant will be. It's just the reciprocal. The secant, just the reciprocal, and the cotangent, just the reciprocal. In right triangles, guys, we're never going to have negative numbers for legs or hypotenuse because we can't have a side that's negative. So that's how it's a little bit different than unit circles. Now, to solve a right triangle means to find all of the parts. We're going to find the 3 angles and the 3 sides. If it's a right triangle, we already know one of the angles is 90. Then it's our task to find the sides and the other 2 acute angles. So, for example, using this figure, we know that this angle's 35 degrees. Well, then I think 90 plus 35 is 125. So beta is equal to 180 minus 125, which is 55. So that takes care of our angles, 55 degrees. Now we got to find B and C. Well, it's up to you how you want to find them. You can either use the 55-degree angle or the 35-degree angle. It's totally up to you. You can't use the 90, that will not work. And the next thing you got to ask yourself is, do you want to use, you have to use 4, obviously, but do you want to find B or do you want to find C? So it's up to you. Totally up to you. So first of all, I'm going to find B. I'm going to go after B. And I'm going to use beta. I'm going to use that 55 because I know 55 is accurate. It's not a decimal. It's not an approximation. So B would be opposite and 4 would be adjacent. Well, opposite and adjacent is OA, so it's tangent of 55 degrees equals B over 4. Then, by using algebra, I got to solve for B by multiplying by 4. So I'm going to multiply both sides by 4. So B is 4 tangent 55. So on my calculator now, I change my mode to degrees. And once I do that, I can type 4 tangent 55 straight into my calculator, and B is approximately 2 decimal places, 5.71. Now, we want to avoid using this number to find C. The reason is because it will be an approximation of an approximation, using an approximation. Now, sometimes we have to do that, but in this case, we don't have to. Because I could use, if I stay with B, or with beta, sorry, if I stay with beta, this is the hypotenuse, and I could use adjacent in hypotenuse, which is cosine. And the cosine of 55 is the adjacent side over the hypotenuse. Now, this looks a little different than the green, than the tangent. Since my denominator now is a variable, it does not change my algebra. I still multiply by the variable, by the denominator. Then I have to divide by cosine 55. Now, the shortcut is known now that when you have a variable in the denominator, you know it's going to be division. And if you do enough problems, you'll understand what I'm talking about. It'll just happen. You'll be able to simplify it really quickly. But C then is approximately 6.97. B is approximately 5.71, and beta is definitely 55. Now, if we chose to use 35, we will get the same answer. Now, I'm going to go ahead and do it quick. If I use 35 and I'm going to find B, then now 4 is the opposite and B is the adjacent. And I'm going to multiply by B and then divide by the tangent of 35. So 4 divided by tangent of 35 should be, on my calculator, should be 5.71. And guess what? It is. So we can either use this or this. It does not matter. Just as long as we choose whatever angle we choose, that's what we go with. Now, similarly, I can find C using using sine, wouldn't it? Sine of 35 would equal 4 over C. And again, multiply by C and then divide by sine of 35. So it's 4 divided by sine 35. And I bet we get 6.97, and we indeed do. 6.97. So there's more than one way to solve a triangle. Now, why do we learn this? Because we can solve problems with right triangles. The first thing we need to do is to draw a picture of it, okay? The second thing we need to do is to write the trig ratio equation, and then the third one is solve it to answer the problem. So here's a problem that's already been drawn for you. 25-foot ladder leans against a wall and forms a 70-degree angle with the ground, okay? How high up the wall is the top of the ladder? So it's our task to figure out the height. Well, we know this is 90, so 70 and h are opposite. So this is the opposite, and we know 25 is our hypotenuse. So we go through SOHCAHTOA, and we know that that's sine, which is the sine of 70 equals h over 25. Multiply by the denominator, 25 sine 70, and that ladder is approximately 23.49 feet up the side of the wall. Okay? Right triangle trig is nice. Okay, Liam is building a skateboard ramp using wooden planks. All right, so we got to draw a ramp. There's the 90. He wants the ramp 4 feet high and an angle of elevation of 20. What we don't know is how long the ramp is. So again, that would be opposite and hypotenuse, wouldn't it? So the sine of 20 now would equal 4 over x. So since the denominator has a variable, we're going to end up dividing instead of multiplying. No big deal. The ramp will be about 11.70 feet long. So if I'm going too fast, just stop it and go over it, okay? The angle of elevation of the sun is 35.1 degrees at the instant the shadow cast by the Washington Monument is 789 feet long. What's the height of the monument? Okay, we know it's an obelisk, okay? So it looks something like this. And we got this big long shadow here. And then we have the sun's rays coming into it. We'll use this, right? That's creating this shadow. Well, we know that this is 90, kind of got a three-dimensional. We know that the angle of elevation is 35.1 degrees. We're supposed to find the height. Oh, forgot one thing. It's 789 feet away from where we're standing, measuring, right? Obviously not to scale, because this would be much taller if my guy was that tall. Okay. So it looks like it's going to be opposite and adjacent, doesn't it? Well, SOHCAHTOA, opposite and adjacent, it's tangent. So the tangent of 35.1 equals h over 7089. There you go. So we're going to take tangent of 35.1 times 789. How tall is the Washington Monument? It is about 554.5 feet according to our measurements. And I don't know the exact height. We could look it up. But that, for what this problem asks, that's a pretty darn good calculation. Okay, a slide on a child's swing set is 6 feet long. Okay, so we know what a slide looks like. Or we should know what a slide looks like. So here's our slide. Pretend that's a 90. It's 6 feet long, and the ladder's 5 feet high. At what angle does the ladder meet with the slide? The ladder meet with the slide. Oh, my bad. That's not 90. This is 90. So I didn't draw it very well. Let's start over. Let's make it so that it looks 90, shall we? Let's do that again. There we go. There's the slide. So this is 5 feet high, and this is 6 feet long. Now I realize there's probably an angle here. It's not exactly 90, but that's okay. We're supposed to find theta. Ooh. What angle does the ladder meet with the slide? Well, this is the ladder, and this is the slide. So the angle right there, that's the theta we're trying to find. Okay, so label these sides. Well, this is opposite, so we don't care. This is always the hypotenuse, and this is the adjacent, so it looks like it's cosine, right? Adjacent and hypotenuse, A-H, SOHCAHTOA. So the cosine of theta equals 5 over 6, adjacent over hypotenuse. Now, here's the problem. We're not finding a side as we did on the rest of these. We are finding an angle. How do you find an angle? I hope you're thinking, wait a minute, to find theta, we have to undo cosine. How do we undo cosine? Inverse cosine. Now, we know this. We just took a test on it not long ago. So the inverse cosine of 5/6 is what we're looking for. So that angle is about 33.6 degrees, or about 34 degrees between the ladder and the slide. Okay, so we can find angles as well using trig, right triangle trig. And here's a great example of that. Adorning the top of the Board of Trade building in Chicago is a statue of Ceres, the Roman goddess of wheat. From street level, two observations are taken 400 feet apart, 400 feet from the center of the building. The angle of elevation to the base of the statue is found to be 55.1 degrees, and the angle of elevation to the top of the statue is 56.5. What's the height of the statue? Okay, so the first thing we need to do is draw some land here. Here's the building. Here's the statue, goddess of wheat, whatever. Okay, we got to go to the middle, and we are 400 feet away. Okay, and I think we measure to the top of the building and to the top of our little lady there, our goddess of wheat. Okay, so I can't find this distance here, what I'm looking for, because this triangle right here, if you look, it is not a right triangle. It is what we call oblique. So right triangle trig doesn't work. SOHCAHTOA doesn't work. But we do know some angles, right? We know that one angle's 55.1. That's this angle. And then the other angle is 56 degrees, right? 56.5 degrees, sorry. 56.5 degrees. Okay, now, why is that important? Well, if I can find this, we'll call it X, and I can find that, we'll call it Y, and then I'll find that Z by taking Y minus X. That will give me Z, won't it? The whole thing minus the building will give me the statue. So we need to use, let's see, what are we going to use? This is adjacent, and this is opposite, isn't it? Both of them. So it's going to be tangent, but it's going to be tangent twice. So the tangent of 56.5 is y over 400, and the tangent of 55.1 is x over 400. And we, in both cases, will multiply by 400 to get rid of that denominator, and that gives us x and y. So 400 tangent 56.5 gives us approximately 604.3, and 400 tangent 55.1 gives us approximately 573.4. We're going to go one decimal place here. So if I subtract those, 604.3 minus 573.4, so if you have these nice calculators, it's real easy. You don't have to type it in. I got about 30.9 feet tall. So that's how tall on the whatever Chicago Board of Trade building, yeah, in Chicago, that's how tall that series is. It's about 31 feet high. Pretty tall. Okay, but it is on top of a 400-foot building. Now the last problem, Yola just planted a hybrid elm, and the nursery claims that the tree grows 12 feet per year. She wants to verify that claim. She walks 100 feet from the base of the tree, and using a transit that is 2 feet off the ground, determines the angle of elevation is 5.7 degrees. 1 year later, the angle of elevation 100 feet from the tree is 11.9 degrees. Did it grow 12 feet? Well, this is what the picture would look like, much like the one we just did. This is 5.7. This is 11.9. the 2 feet is kind of negligible. We don't even really need that with the ground. But we can't find H and G, can we? Well, we can find H, but we can't find G until we find, let's call it J. And then G would equal J minus H. So let's look at this then. Would this also be tangent? I believe it is. This is opposite and adjacent again. So the tangent of 11.9 degrees equals J over 100. So multiply by 100. So 100 tangent 11.9 is about 21.07 feet. And then the tangent of 5.7 degrees equals H over 100. Multiply by 100. 100 tangent 5.7 is about 9.98 feet. So if we subtract those two, we get 11.1 feet, which is still pretty good, isn't it? So this minus 9.98, I guess. However, their claim was 12 feet. We are 0.9 feet off. So that is not true. They lied. Well, not really. So we have a worksheet over right triangle trig. Make sure you ask questions if you don't understand something.